The data networks that we use in our everyday lives to learn, play, and work range from small, local networks to large, global internetworks. At home, you may have a router and 2 or more computers. At work, your organization may have multiple routers and switches servicing the data communication needs of hundreds or even thousands of PCs. In the previous chapters you discovered how routers are used in packet forwarding and that routers learn about remote networks using both static routes and dynamic routing protocols. You also know how routes to remote networks can be configured manually using static routes. This chapter introduces dynamic routing protocols, including how different routing protocols are classified, what metrics they use to determine best path, and the benefits of using the dynamic routing protocol. Dynamic routing protocols are usually used in larger networks to ease the administrative and operational overhead of using only static routes. Typically, a network uses a combination of both a dynamic routing protocol and static routes. In most networks, a single dynamic routing protocol is used. However, there are cases where different parts of the network may use different routing protocols. Since the early 1980s, several different dynamic routing protocols have emerged. In this chapter we will begin to discuss some of the characteristics and differences in these routing protocols. However, this will become more evident in later chapters when we discuss several of these routing protocols in detail. Although many networks will only use a single routing protocol or use only static routes, it is important for a network professional to understand the concepts and operations of all the different routing protocols. A network professional must be able to make an informed decision regarding when to use a dynamic routing protocol and which routing protocol is the best choice for a particular environment. The evolution of dynamic routing protocols. Dynamic routing protocols have been used in networks since the early 1980s. The first version of RIP was released in 1982. But some of the basic algorithms within the protocol were used on the ARPANET as early as 1969. As networks have evolved and become more complex, new routing protocols have emerged. The figure shows the classification of routing protocols. One of the earliest routing protocols was Routing Information Protocol RIP. RIP has evolved into a newer version RIP v2. However, the newer version of RIP still does not scale to larger network implementations. To address the needs of larger networks, two advanced routing protocols were developed: Open Shortest Path First OSPF and Intermediate System to Intermediate System is. Cisco developed Interior Gateway Routing Protocol IGRP and Enhanced IGRP which also scales well in larger network implementations. Additionally, there was the need to interconnect different internetworks and provide routing among them. Border Gateway Routing BGP protocol is now used between ISPs as well as between ISPs and their larger private clients to exchange routing information. With the advent of numerous consumer devices using IP, the IPv4 addressing space is nearly exhausted. Thus IPv6 has emerged. To support the communication based on IPv6, newer versions of the IP routing protocols have been developed. See the IPv6 road in the table. Note: this chapter presents an overview of the different dynamic routing protocols. More details about RIP, the IGRP, and OSPF routing protocols will be discussed in later chapters. The ISIS and BGP routing protocols are explained in the CCNP curriculum. IGRP is the predecessor to EIGRP and is now obsolete. A role of dynamic routing protocol. What exactly are dynamic routing protocols? Routing protocols are used to facilitate the exchange of routing information between routers. Routing protocols allow routers to dynamically share information about remote networks and automatically add this information to their own routing tables. This is shown in the animation. Routing protocols determine the best path to each network which is then added to the routing table. One of the primary benefits to using the dynamic routing protocol is that routers exchange routing information whenever there is a topology change. This exchange allows routers to automatically learn about new networks and also to find alternate paths when there is a link failure to a current network. Compared to static routing, dynamic routing protocols require less administrative overhead. However, the expense of using dynamic routing protocols is dedicating part of a router's resources for protocol operation including CPU time and network link bandwidth. Despite the benefits of dynamic routing, static routing still has its place. There are times when static routing is more appropriate and other times when dynamic routing is the better choice. More often than not, you will find a combination of both types of routing in any network that has a moderate level of complexity. We will discuss the advantages and disadvantages of static and dynamic routing later in this chapter. The purpose of dynamic routing protocols. The routing protocol is a set of processes, algorithms, and messages that are used to exchange routing information and populate the routing table with the routing protocol's choice of best paths. The purpose of a routing protocol includes discovery of remote networks, maintaining up-to-date routing information, choosing the best path to destination network's ability to find the new best path if the current path is no longer available. What are the components of a routing protocol? Data structures. Some routing protocols use tables and /or databases for its operations. This information is kept in RAM, algorithm. An algorithm is a finite list of steps used in accomplishing the task. Routing protocols use algorithms for facilitating routing information and for best path determination. Routing protocol messages. Routing protocols use various types of messages to discover neighboring routers, exchange routing information, and other tasks to learn and maintain accurate information about the network. Dynamic routing protocol operation. All routing protocols have the same purpose, to learn about remote networks and to quickly adapt whenever there is a change in the topology. The method that a routing protocol uses to accomplish this depends upon the algorithm it uses and the operational characteristics of that protocol. The operations of a dynamic routing protocol varies depending upon the type of routing protocol and the routing protocol itself. In general, the operations of a dynamic routing protocol can be described as follows. The router sends and receives routing messages on its interfaces. The router shares routing messages and routing information with other routers that are using the same routing protocol. Routers exchange routing information to learn about remote networks. When a router detects a topology change, the routing protocol can advertise this change to other routers. Play the animation to see dynamic routing protocols in operation. Note: understanding dynamic routing protocol operation and concepts and using them in real networks requires a solid knowledge of IP addressing and subnetting. 3 subnetting scenarios are available at the end of this chapter for your practice. Static routing usage. Before identifying the benefits of dynamic routing protocols, we need to consider the reasons why we would use static routing. Dynamic routing certainly has several advantages over static routing. However, static routing is still used in networks today. In fact, networks typically use a combination of both static and dynamic routing. Static routing has several primary uses, including providing ease of routing table maintenance in smaller networks that are not expected to grow significantly. Routing to and from stub networks. See Chapter 2. Use of a single default route, used to represent the path to any network that does not have a more specific match with another route in the routing table. Static routing advantages and disadvantages in the table. Dynamic and static routing features are directly compared. From this comparison, we can list the advantages of each routing method. The advantages of one method are the disadvantages of the other. Static routing advantages: minimal CPU processing, easier for administrator to understand, easy to configure. Static routing disadvantages: configuration and maintenance is time-consuming. Configuration is error-prone, especially in large networks. Administrator intervention is required to maintain changing route information. Does not scale well with growing networks. Maintenance becomes cumbersome. Requires complete knowledge of the whole network for proper implementation. Dynamic routing advantages and disadvantages. Dynamic routing advantages: administrator has less work maintaining the configuration when adding or deleting networks. Protocols automatically react to the topology changes. Configuration is less error-prone. More scalable. Growing the network usually does not present the problem. Dynamic routing disadvantages: router resources are used, CPU cycles, memory and link bandwidth. More administrator knowledge is required for configuration, verification, and troubleshooting. Interior gateway protocols. IGPs can be classified as 2 types: Distance vector routing protocols. Linked state routing protocols. Distance vector routing protocol operation. Distance vector means that routes are advertised as vectors of distance and direction. Distance is defined in terms of a metric such as hop count, and direction is simply the next hop router or exit interface. Distance vector protocols typically use the Bell-Manford algorithm for the best path route determination. Some distance vector protocols periodically send complete routing tables to all connected neighbors. In large networks, these routing updates can become enormous, causing significant traffic on the links. Play the animation to see the operation of distance vector routing protocols. Although the Bell-Manford algorithm eventually accumulates enough knowledge to maintain a database of reachable networks, the algorithm does not allow a router to know the exact topology of an inter-network. The router only knows the routing information received from its neighbors. Distance vector protocols use routers as signposts along the path to the final destination. The only information a router knows about a remote network is the distance or metric to reach that network and which path or interface to use to get there. Distance vector routing protocols do not have an actual map of the network topology. Distance vector protocols work best in situations where the network is simple and flat and does not require a special hierarchical design. The administrators do not have enough knowledge to configure and troubleshoot linked state protocols. Specific types of networks, such as hub and spoke networks, are being implemented. Worst-case convergence times in the network are not a concern. Distance vector routing protocol functions and operations will be explained in the next chapter. You will also learn about the operations and configuration of the distance vector routing protocols RIP and EIGRP. Linked state protocol operation. In contrast to distance vector routing protocol operation, the router configured with a linked state routing protocol can create a complete view or topology of the network by gathering information from all of the other routers. To continue our analogy of signposts, using a linked state routing protocol is like having a complete map of the network topology. The signposts along the way from source to destination are not necessary, because all linked state routers are using an identical map of the network. A linked state router uses the linked state information to create a topology map and to select the best path to all destination networks in the topology. Play the animation. With some distance vector routing protocols, routers send periodic updates of their routing information to their neighbors. Linked state routing protocols do not use periodic updates. After the network has converged, a linked state update only sent when there is a change in the topology. For example, the linked state update in the animation is not sent until the 172.16.3.0 network goes down. Linked state protocols work best in situations where the network design is hierarchical, usually occurring in large networks. The administrators have a good knowledge of the implemented linked state routing protocol. Fast convergence of the network is crucial. Linked state routing protocol functions and operations will be explained in later chapters. You will also learn about the operations and configuration of the linked state routing protocol OSPF. Classful routing protocols. Classful routing protocols do not send subnet mask information in routing updates. The first routing protocols such as RIP were classful. This was at a time when network addresses were allocated based on classes, class A, B, or C. The routing protocol did not need to include the subnet mask in the routing update because the network mask could be determined based on the first octet of the network address. Classful routing protocols can still be used in some of today's networks, but because they do not include the subnet mask they cannot be used in all situations. Classful routing protocols cannot be used when a network is subnet using more than one subnet mask. In other words, classful routing protocols do not support variable length subnet masks (VLSM). There are other limitations to classful routing protocols, including their inability to support discontiguous networks. Classful routing protocols, discontiguous networks and VLSM will all be discussed in later chapters. Classful routing protocols include RIP-1 and IGRP. Classless routing protocols. Classless routing protocols include the subnet mask with the network address in routing updates. Today's networks are no longer allocated based on classes and the subnet mask cannot be determined by the value of the first octet. Classless routing protocols are required in most networks today because of their support for VLSM. discontiguous networks and other features which will be discussed in later chapters. In the figure, notice that the classless version of the network is using both /30 and /27 subnet masks in the same topology. Also notice that this topology is using the discontiguous design. Classless routing protocols are RIP2, IGRP, OSPF, this is BGP. Convergence is when all routers' routing tables are at a state of consistency. The network has converged when all routers have complete and accurate information about the network. Convergence time is the time it takes routers to share information, calculate best paths, and update their routing tables. A network is not completely operable until the network has converged, therefore, most networks require short convergence times. Convergence is both collaborative and independent. The routers share information with each other but must independently calculate the impacts of the topology change on their own routes. Because they develop an agreement with the new topology independently, they are said to converge on this consensus. Convergence properties include the speed of propagation of routing information and the calculation of optimal paths. Routing protocols can be rated based on the speed to convergence. The faster the convergence, the better the routing protocol. Generally, RIP and IGRP are slow to converge, whereas the IGRP and OSPF are faster to converge.